Assalamualaikum and hi guys. Let us learn chapter 2, Capacitor and Dielectrics. Learning outcome 2.1 is Capacitance and Capacitors series and parallel. At the end of this chapter, you should be able to define and use capacitance C equal to Q over V. You need to derive and determine the effective capacitance of capacitors in series and parallel, and derive and use energy start in capacitor. We have three equations related to energy start. You can use half CV square, half QV, and half Q square over C. The capacitor is a component which has ability or capacity to store energy in the form of electric charge. So it producing a potential difference across its plates. It's much like a small rechargeable battery. And it consists of a pair of conducting plates separated by insulator, and the insulator is called a dielectric, okay, and it's often like an air, oil, or paper. All these are types of insulator inside the capacitor. Now let us learn about capacitance. Capacitance is the amount of charge that a capacitor can store per unit of voltage across its plates, or we can say ratio of the magnitude of the charge on either plate to the potential difference between them. And the capacitance is designated as a C equal to Q over V. The greater the charge that a capacitor can store for a given voltage, the higher capacitance value. Q is then for charge on one of the plates. V is the potential difference across them. And unit of capacitance is coulomb per volt, or you can use unit farad or capital F. Let us describe about 1 farad. 1 farad is defined as the charge of 1 coulomb stored on each conducting plate as a result of potential difference of a 1 volt between the two plates. So, from the equation we have C equal to Q over V means that 1 coulomb of charge, or 1 coulomb divided by 1 volt of potential difference, you will get 1 farad. That is the value for 1 farad of capacitance. And the capacitance for a capacitor does not change unless it is designed to be variable capacitor. Right, from the equation Q equal to CV, if we constant the capacitance, Q is proportional to V. If V increase means Q also increase. In another words, we can say the charge stored, or Q, is directly proportional to the potential difference across the conducting plates. So if you have a large of capacitance or greater capacitance, you need more charge to insert in the capacitor. Here are arrangement of capacitors in series. If you look at this circuit, we have C1, C2, and C3. this capacitance, we can add all C1, C2, and C3, and it become as C effective. So when the circuit is complete like this, once we close the switch, okay, the electrons will be transferred onto these plates, okay, that the magnitude of the charge Q on each plate must be same. The total charge of effective capacitor is equal to Q. Q, or sometimes we use Q effective or Q total, equal to Q1. Q1 equal to Q2, and Q2 also equal to Q3. Means that all the charges here have same value. However, for the potential difference across each capacitor C1, C2, and C3, the V1, V2, and V3 will different. We have V1 equal to Q1 over C1. However, since we know the Q1 is same like Q, we just can put it as a Q over C1. Same also for V2. V2 equal to Q2 over C2. As we all know, Q2 equal also to Q over C2. And V3 equal to Q3 over C3, which also equal to Q over C3. The total potential difference V is given by V equal to V1 plus V2 plus V3. This is for series capacitor in series. So V equal to, we substitute from the equation V, Q over C. C is referred to C1 plus Q over C2 plus Q over C3. Right? So from here, we rearrange from V over Q here. You will get 1 over C1 plus 1 over C2 plus 1 over C3. And 1 over C1 plus 1 over C2 plus 1 over C3 is equal to 1 over C effective. So we can say here the 1 over C effective is equal to 1 over C1 plus 1 over C2 plus 1 over C3, which showing us capacitor in series. Capacitors in parallel. This figure shows capacitors which connected in parallel. It's showing that we have C1, C2, and C3, which refer to the naming of capacitors. For C1, it have V1. V1 is a V1, or every potential across each capacitor have a same power supply voltage. Means that V here supplied to V1 have the same voltage. V2 equal to V1, and V2 also equal to V3. Means we can say V total here is equal to V1 equal to V2 equal to V3. That is capacitors in parallel. Since you all know the potential difference on the effective capacitor is V equal to V1 equal to V2 and equal to V3. So the charge stored by each capacitor C1, C2 and C3 are Q1, Q2 and Q3. So we can put here Q1 equal to C1 V1, which equal to C1V. You can also use the same method for Q2, which equal to C2V2, which also equal to C2V. And for Q3 also same, C3V3, which equal to C3 times V. The total charge Q on effective capacitor is given by Q equal to Q1 plus Q2 plus Q3. So, by take out the equation from Q1, Q equal to C1V plus C2V. Why we are not put V1? Because it have same value, and plus C3V. So we rearrange here as a Q over V equal to C1 plus C2 plus C3. Okay, if you notice that C1, C2, C3 is C effective. So we can say that Q over V is equal to C effective. Therefore, the effective equivalent capacitance or C effective for capacitors in parallel, we can directly use C effective equal to C1 plus C2 plus C3 and so on. So this is capacitors in parallel. Energy stored in a charged capacitor. When the switch is closed, actually the charges begin to accumulate to the capacitor plates. So a small amount of work needed to bring a small amount of charge from the battery to the capacitor plates. So how to express this equation? By using delta work done equal to V delta Q. Since you know the C equal to Q over V, since you know C equal to Q over V, we are just substitute V here as a Q over C times delta Q, which is equal to delta work done. While capacitor is connected across a battery, charges come from the battery and get stored in the capacitor plates. This process of energy storing is step by step only. At the very beginning, capacitor does not have any charge or potential. Now, at the time of switching, or we close the switch, full battery voltage will fall across the capacitor. Total work required to increase the accumulated charges from 0 to Q is given by work done equal to integration between 0 to Q in between V dq, which equal to, we integrate from 0 to Q, V itself is equal to Q over C dq, right? So from here, 1 over C, we factorize it, 1 over C from 0 to Q, and Q dq, which equal to 1 over C times Q square over 2. So you will get work done which equal to half Q square over C. Guys, we know that Q equal to CV. Okay, so work done is equal to half CV square. We rearrange from half CV square from the C equal to Q over V. Okay, so you will get work done also equal to half QV. And the work done in bringing the capacitance actually appears as electric potential energy stored. So we can say the work done or W is equal to energy. So we can say U also equal to half CV square. U equal to half QV and U equal to half Q square over C. So we have three equations that you can use as a work done or energy stored in capacitor. Our learning outcome 2.2 is charging and discharging of capacitors. So you need to state physical meaning of time constant and use tau equal to RC. And then the second one, you need to sketch and explain the characteristics of charge against time graph and current against time graph for charging and discharging of capacitor. And you need to use Q equal to Q naught epsilon negative T over RC for discharging and Q equal to Q naught 1 minus E negative T over RC for charging. Charging and discharging of capacitors. Actually, we have two main process for capacitors, which we have charging process and discharging process. And the time constant is very important in capacitor because it can detect how fast a capacitor to get charged or discharged. And the symbol that we use for time constant or tau is expressed as a T equal to RC. This is the diagram for charging capacitor. So we have, this is the basic circuit for charging of a capacitor. We have battery, we have switch, and we have resistor with the capacitor here. And this is simulation for charging process, where the electrons flow out from negative terminal. The negative electron move to these plates. Okay, the Q increase, and until it reach the maximum, which equal to V naught here, and at that time no current flows through the resistor. So then the charge on the capacitor reach Q naught or Q maximum. So this process, we call it as a charging process. This is a charging graph and its formula. Okay, if you look at this graph, it's showing that graph Q against T, where the time constant for charging process is at 0.63 out of Q naught. And you can use the equation for charging graph where Q equals to Q naught 1 minus epsilon negative T over RC. And the Q naught is referred to maximum charge, R is resistance of resistor, and C is the capacitance of capacitor. Alright, this is charging process for current. Current against time graph showing that the current through resistor decrease exponentially and the time constant for current reduced is 0.37 from I naught. So that is the time constant for current. And V naught is referred to the maximum voltage or equal to supply voltage. I naught is the maximum current. R is referred to the reference resistance of the resistor, and C is the capacitance of capacitor. For discharging a capacitor through a resistor, I show you a simple figure which shows simple circuit for discharging charge capacitor. So this switch is closed and electrons from plate P begin to flow through resistor R and neutralize positive charges at plate A. This is discharging graph. You can see graph Q against time, where the charge on the capacitor decreases exponentially with the time. And you can see the formula of discharging for charge Q equal to Q naught epsilon negative T over RC. Q naught is referred to the maximum charge, R is resistance of the resistor, and C is the capacitance of the capacitor. This is discharging graph for current against time, where the current through the resistor decreases exponentially with the time. The formulas for discharging current is I equal to negative I naught epsilon negative T over RC, where the I naught is also equal to Q naught over RC. The Q naught is the maximum charge. R is resistance of the resistor and C is capacitance of capacitor. If you look at, we have negative sign at this equation. It's referred to the current direction, which is opposite to its direction when the capacitor was being charged. So, in calculation, the negative sign we can be ignored. This is a graph of charging capacitor. We have three types of graph, Q against T, V against T, and I against T. But if you look at the I against T, we have a different graph because of I equal to I naught epsilon negative T over RC. Okay, this is the current decreasing exponentially for charging capacitor. This is graph discharging capacitor. So you can see for Q against T, the graph Q, the charge is decreased exponentially with the time. However, for V also same, we decrease exponentially with the time. But for I against T, the graph is negative. The negative I naught is decreased exponentially with the time, but at negative I naught. Time constant. Time constant is a measure of how quickly the capacitor charges or discharges, and it is a product from resistance and capacitance. It is a scalar quantity with the unit seconds. So this is the symbol for tau. Tau equal to RC. For charging process, the time required for capacitor to reach 63% of its maximum charge, whereas for current, it is the time required for current to drop 37% of its initial value or I naught. However, for discharging process, it is time required for a charge on the capacitor or voltage or current in a resistor decreases to 37% of its initial value. How fast a capacitor to get charged depends on the time constant. So by referring to the formula tau equal to RC, if you increase the resistance and capacitance, the time constant will increase. So, if you have C or capacitance larger, you will take a longer time to charge a capacitor. And if you have a resistor, higher of resistor, the current in the circuit is lower, so you also will take a longer time to get charged. The last subtopic is capacitors with dielectrics. You need to define a dielectric constant, epsilon r equal to epsilon over epsilon naught. You need to describe the effect of dielectric on a parallel plate capacitor. You have to calculate the capacitance of a filled parallel plate capacitor. You have to use dielectric constant and use capacitance with dielectric. This is parallel plate capacitor. We have two plates which the area is parallel to another plates, and it is separated by distance. We use symbol D here, and these two plates also, in between these two plates we have a vacuum or air, and these plates also have charge which equal to the magnitudes but in opposite direction. So we have positive Q and negative Q. The positive Q is attached or connected with the positive terminal, and negative Q is connected with negative terminal. So then we have potential difference across the plates. This is parallel plate capacitor, and these two plates is very close each other. So we can assume the electric field is uniform between the plates. Since the distance between the plates is lesser than area, so the electric field strength or E between the plates is uniform. So the magnitude of this electric field strength within the plates is given by E equal to sigma over epsilon naught, and the sigma is equal to Q over A. So we substitute from the equation of electric field strength equal to Q equal to sigma over epsilon naught. You will get Q over area times epsilon naught. And you have to know what is sigma. Sigma is the surface charge density on either plate, and the unit is coulomb per meter square, and it is a scalar quantity. From the previous equation just now, we have E equal to Q over area times epsilon naught, and we expand from this equation, E equal to CV. Because of Q equal to CV, we substitute here, over area times epsilon naught, and V itself is equal to ED. So we can use C times V or ED over A times epsilon naught. So if we have case for separated by dielectric material, okay, if it is separated by dielectric material, third by dielectric material, we can use C equal to epsilon A over D. Or if the case is separated by vacuum, okay, so you can use the formula C equal to epsilon naught A over T. So this is the epsilon naught, which is referring to the permittivity of free space. Epsilon is permittivity of dielectric material, and D is the distance between the two plates, and the last is area, which is A, area of each plate. This is dielectric constant, and the symbol is epsilon R. R is referred to relative permittivity, and it is the ratio of capacitance of a capacitor when dielectric between the plates of capacitance of capacitor have a free space between its plates. And you can see this is the meaning of epsilon R, C, and C naught. So I hope that you understand. This is the equations of capacitance and the permittivity of dielectric. So we can correlate between C over C naught, which equal to epsilon over epsilon naught. And besides that, we can also find the epsilon relative, which equal to epsilon over epsilon naught. So with another words, we can put here is also equal to epsilon R. In previous slide, you all know the dielectric is the insulating material such as rubber, plastic, wax paper, mica, and so on, and it has higher electrical resistivity but inefficient supporter. Of course, it can store energy or charge and able to dissipating minimal energy in the form of heat. Besides, it depends on the factor of K, so it will increase a capacitance and increase the charge storage capacity of capacitor. K is also called dielectric constant and relative permittivity. If the gaps between the plates is not a vacuum, but we inserted a dielectric such as mica here, we have to use permittivity dielectric, which is given by epsilon r equal to epsilon over epsilon naught, and we can rearrange the formula as a epsilon r epsilon naught is equal to epsilon. This is the equation that you have used for capacitance if we have inserted any insulator. We use epsilon r epsilon naught A over D to replace epsilon. And the epsilon is dielectric permittivity, which is epsilon is always greater than epsilon naught, and epsilon r is referred to the relative permittivity, such as for mica is 7 and pepper is 3.7.
Let's see guys what happened once we attach this dielectric at plate capacitor. We will see the changes of stored energy. Here I choose parameters capacitance, plate charge and stored energy, and I set dielectric constant 5. This battery already connected, so now I disconnect it and I set the battery at 0 volt. And now I insert this dielectric between the plates capacitor, and once I increase the voltage, stored energy from this yellow bar increase. Once I increase potential, we can see here increasing of number of charges through plate capacitor and dielectric. This is why dielectric is really important, because it can increase the amount of stored charges in capacitor.
However, we have to concern with the pitfall prevention. We have to check either the capacitor connected to a battery first. If it is disconnected from the battery, Q remain same. However, if the capacitor remain connected to the battery while modifications, V remain same. Thank you for listening chapter 2, and bye.